Welcome to Advanced Statistical Physics, online part of the course, lecture number 7, and its subject Electromagnetism 2, strong fields. This is a brief contents of the lecture. I've started electron energy spectrum in strong magnetic field, proceed to summation formula, consider Landau potential for strong magnetic field. As a result, I will derive formula for the Haas van Alphen oscillations, and at the end, it's a bonus part. I will give you a little bit of history in the flow of times. So let's proceed. Magnetism of electron gas in strong magnetic field. And what is strong magnetic field? It is magnetic energy, energy of the spin magnetic field, and orbital frequency of orbital energy too significantly exceeds thermal energy. But under any realistic fields, the magnetic energy will be still much less than thermal energy. So orders of magnitude. So if this temperature is 10 Kelvin, for example, 1 Kelvin. 1 Kelvin 10 to minus 4 electron volt. So this would be, this will be 100 micro electron volt. This will be milli electron volt, 10 milli electron volts. This is 10 electron volts. Those are the typical values of energy. Micro, milli, and 10 electron volts. Under this condition, the orbital magnetism and spin magnetism are not additive. I need to consider them together to find the full spectrum of electron and to find the effect of magnetic field. So electron spectrum is characterized by 3 quantum numbers. This pz, momentum of the motion in direction of magnetic field, and its principal quantum number of Landau oscillator, and plus minus corresponds to projection of the spin. This expression is as kinetic energy, free electron. This is h by cyclotron frequency. This is frequency of Landau oscillator, and this is frequency. And this is energy. It's not frequency. This is energy of Landau oscillator, h omega c, and this is energy of the spin in the magnetic field. Mu b is Bohr magneton. Plus minus corresponds to projection of the spin on direction of magnetic field, along and across and against. In such a case, we obtain grand canonical potential by normal formula. This is summation over all quantum numbers. Px also is present, though energy doesn't depend on px. We know that this degeneracy for the motion in the x direction. And this degeneracy is given by this factor of degeneracy, also called statistical weight. It's proportional to flux of magnetic field divided by unit flux, as we know. This is total energy of the electron, with minus sign, translational, oscillatory motion, spin, this chemical potential for this temperature. So I'm repeating the formula for the grand canonical or Landau potential. It's right here. Now let's affect the summation. And you need to sum over n and plus minus together. As I explained, the effects of orbital motion and spin motion do not separate in the strong fields. So let us look how the summation looks. So I give you a table. In this column I have principal quantum number of Landau oscillator. This column I give projection of the spin. They will alternate, minus, plus, minus, plus. This column I give you this total, this parenthesis that determines the energy. Let's start with the ground state of Landau oscillator, n equals 0. Take minus sign here, and I'll give, of course, 0 here, 0 here, result is 0. Now, let's proceed to the same value of the principal quantum number 0, but take plus for the spin the 0, 1 plus 1, 2 divided by 2 is 1. That's a 1. And then we'll take next n equal 1, but minus sign for the spin. 1, 1 minus 1, this gives you 0. I get again 1. So we have some system appearing. Not go to the same principal quantum number oscillator, but take spin plus. So this is 1. 1 plus 1, 2 divided by 2 is 1. And I'm getting 2. Now let's take principal quantum number as 2, but spin minus 1, and I'm getting again 2. So you see, this certainly will continue. And the emerging order is the following. The value 0 for the energy, this parenthesis, occurs only once, but every other 1, 2, and 3 occurs 2. So I see that there will be summation when 0 value of energy is non-degenerate and all others are double degenerate. Repeated twice. That's right. So similar to the previous lecture, we introduced functions, exactly the same function as was in the previous lecture. This function of mu and coefficient absorbs whatever we can absorb in a general form. So the difference is that I exclude magnetic energy, I have only kinetic energy and mu. And to include magnetic energy, I need to shift mu by the amount of magnetic energy. This is exactly like we did before. It's exactly the formula for omega. And there's no summation of px. Summation of px is taken into account by the degeneracy factor, which is already in the formula. It's in a mu bb and in this coefficient, degeneracy factor. So we rewrite this expression specifically. We know now that value n, the value of this parenthesis 0, occurs only once. I'll write 2, and here I'll have to write 1/2 this function. And all others repeated twice, so they go with 2. Those are from n to infinity. So n here is the value of this parenthesis, not the value of this n. But it doesn't matter how you denote the summation variable. It's a mu to down variable, it's just placeholder. As we know, it doesn't make any sense. Doesn't make any difference how do we denote it. I keep denoted as n. So summation runs over all integer numbers. 0 once and all others twice. Of course, numbers are positive here. Now we'll derive a pertinent summation formula. First, we notice that if I take this sum of delta functions shifted by integer and sum over all integers from minus infinity to infinity, it is a periodic function of x with a period of 1. As every periodic function, it can be expanded into Fourier series. And the expansion formula is very easy to obtain from the general formulas for Fourier series. This is a summation of exponentials with the coefficients of 1. It's like delta function, continuous delta function will be integral, and discrete delta function will be summation. So you can check this formula yourself. It's just expression of this 1 it's a coefficient of Fourier series you can compute from general formulas. You can find in any book on calculus. I'm not repeating it here. You're supposed to know it. What we do, we'll multiply left-hand side by some function f of x is smooth enough with respect to this delta function, the regular function f of x, and integrate. So if I take in n equals 0, that is only once in this formula, And I will integrate from 0 to x, 0 to infinity, not from minus infinity to infinity. This function. So when I consider n equals 0, integration goes from 0. It is integration over only half of the delta function. The whole delta function will be for some small number negative to some small number positive, from minus infinity to plus infinity. It would be give you 1, and this is only half of it, so I'm getting 1/2 f of 0. All others delta functions are integrated completely, and then I'm replacing x by number n. This is sum over n. This is exactly the structure I need here. So I need to find integral over all positive numbers from the function, and with this periodic delta function, the result will be exactly what I need for calculation of the grand potential. Repeating the last formula, this is summation formula. I'm comparing to the expression for omega, which is equation 6 on the previous slide. We see that if you set f of x equal to mu bb, this is energy Landau oscillator, but our function f, to introduce the last lecture and repeat it here, then the right hand side become exactly expression for omega. Left hand side, this one, give the expression of it in the integral form right here. So this is the term corresponding to n equals 0, and the second term we pair terms with k and minus k, because summation goes from k from minus infinity to infinity, and every non-zero k repeated twice, as we know. So k comes here, and minus k is complex conjugate of this exponential. Together they will give you double real part of the exponential. This exact expression. We didn't do any approximation. Just rewrote it using theory Fourier series. Now in the first term we will do familiar substitution. We'll call argument as a new variable, z, defined as mu minus 2 mu bb x, that's this argument. dz, the variable is x, so dz is minus 2 mu bb dx. Minus sign means that I will have to swap limits of integration. What are limits of the integration? When x equals 0, then z is equal mu. When x equal infinity, then z is minus infinity. And we rewrite this equation as the following. So the first term contains integral omega naught is integral from minus infinity to mu. It does not depend on magnetic field. So this is Landau potential at b equals 0. It's very similar to weak fields. The first term is independent magnetic field. The second term gives a dependence on magnetic field. It is not a correction, it is maybe big quantity. We do not assume any perturbation theory here. We sum exactly, and this is just the sum. Repeat it. Okay, I'm repeating the last formula. This is Fourier series expression for the Landau potential. We recall definition f of mu that was introduced in the last lecture, lecture number 6, and repeated in this lecture as equation number 4. Then we write this equation Tn as omega naught. This coefficient comes mostly from f, real part of some of the certain integrals ik, and ik is, this coefficient will be absorbed by one of the integrations. Integral dx, this integral. Integral dpz comes from definition of f. That was function that was in the definition of f. Now for this integration dx, we'll substitute x by epsilon, and epsilon will be this argument. So d epsilon is this, for this integration, this is a constant, 2 mu b dx. We'll exchange order of integration, like dpz external integration, dx internal integration, which is possible because integrand is regular and integrals are converging. We'll obtain ik is minus, now integral dpz, and what depend of dpz, this multiplier. Integral over the epsilon runs when x is equal 0. This is 1 over 2m pz squared. When x is infinite, it is infinity. So integral from 1 over 2m pz squared the epsilon, and integrand contains what comes from x, definition of x, and this one with pz we took outside, it doesn't depend on x. And this argument of the exponential exponent become mu minus epsilon divided by kbt. Now this first integration limits pz squared over 2m to this value. If so, the argument of this exponential is another 1, it gives a significant contribution to the integral. If pz is much greater than that, this phase is very large. Exponential of I by phase oscillates very rapidly, canceling different periods, so it doesn't accumulate. So the actual effective value given contribution to this integral are on order of pz squared kinetic energy of electron, on order of magnetic energy. Now, in the second integral, epsilon contributes with very close to mu, so electrons very close to Fermi surface only contribute, and the interval, width of the interval is very small, kbt, the smallest quantity in this problem. This value, pz squared, is on order of the magnetic field, as we know from the first integral, is much smaller than mu. So epsilon is close to mu, but lower limit of epsilon is much smaller than mu. It doesn't matter how much smaller, you can safely replace it by 0. So doing so, obtain the next formula. dpz, as used to be, runs from minus infinity to infinity, but epsilon is from 0 to infinity. So in this form, the integral can be calculated. So first integral separates, because second integral doesn't contain pz anymore. It eliminated from the lower limit. And it is not absolutely converging integral. It can be calculated by regularization. So I regularize changing I to I minus alpha when alpha is positive and infinitesimal constant. So it's actually limit when alpha equals to 0. This is how this integral should be understood. Then this integral converges and becomes a Poisson integral. And this is value of Poisson integral. So it contains square root of I minus alpha. And the square root of I minus alpha can be calculated the following way. This constant I minus alpha, because alpha is very small and positive, it lies in the second quadrant of the complex plane. It's positive imaginary part, negative real part. In fact, this quadrant possesses phases between pi and pi over 2. Actually, because alpha is equal to 0, the argument very close to I, so argument is close to pi over 2. Square root has half of phase, so it's very close to pi over 4. So if I neglect now alpha, it gives me pi over 4. So this argument with alpha, it eliminates uncertainty plus minus before radical. It can be plus minus I pi over 4. So this principle that we used, limit, fixes the sign. So this is a very well-known approach to regularization of such oscillating integrals, which is used in a different area of physics. In this particular, very often in WKB approximation in quantum mechanics, this jumps of sign is called the Stokes phenomenon. It's very common. So Landau very well knew about that and used it. So, and he, by the way, did not describe in this book this. It is considered as a necessary in the arsenal of a theoretical physicist. So every theorist should know that. So hence we get equation 15 minus, because this was in the denominator, substituted here the equation for IK, equation 14, and obtain. So this value of IK, so this is the phase that came from the Poisson integral. This is the value that came from Poisson integral. This is the rest of it. Now this integral can be actually calculated exactly, but we only interested in oscillating term. We don't interested in smooth pedestal. Our goal is to find oscillating contribution to all physical quantities that we will be using. So we integrated by part. Take this exponential under d and divide by this coefficient. That is divided by this coefficient. We will get term that it is product of the functions, this term. Double substitution from 0 to infinity. In neither of these limits it oscillates. So this is it's smoothly dependent on parameters. Magnetic field, it doesn't oscillate. So this term minus term in the integration by parts, this term oscillates, this minus term. So this is derivative of logarithm. Give me argument of logarithm. This derivative of argument, which is exponential, over its argument. And finally, derivative of the argument, mu minus epsilon kbt over the epsilon give me minus. That give me total sign plus. So this is this expression. So I am neglecting the non-oscillating term, not because it is small, but it doesn't oscillate. I don't care about it. So neglecting it, I'm getting IK in this form. So this integral only left. Now I will divide numerator and denominator by this quantity. So it appears in denominator with opposite sign of exponent. This trick very well known to us. And then get the integral of type of Fermi distribution. Integral of the Fermi distribution. What is in denominator? This factor is Fermi distribution. Now we need to affect this integral and we will integrate by parts. Here repeating the last formula. We integrated by parts again. Taking this exponential under the differential, which compensating coefficient will be mu bb, increases power mu bb to 5/2, divided by I pi k. I and I give me -1, together will be plus. I increases power of pi to 2, and power of k increases from 3/2 to 5/2. One differentiation of this give me minus, and then minus in the formula of the integration by parts give me another minus. So altogether sign will be plus. This expression will make a substitution calling argument of this exponential. So epsilon is equal to kbt psi plus mu. And mu is of course constant. Kbt is constant. So the epsilon is kbt d psi. We substituted here. So it does give me extra coefficient. The epsilon give me kbt, extra kbt. So kbt instead of square becomes back 1. This exponential becomes e to the power of psi. This is e to the power of psi plus 1 squared. And this argument here from epsilon acquires addition of mu. And this with epsilon replaced by mu does depend on integration variable, so it can be taken outside. This is this coefficient mu divided by mu bb. Lower limit of this integral when epsilon is equal 0, it is minus mu divided by kBt. When epsilon is equal infinity, it is infinity. Now pay attention that psi in this formula is very close to 1, because if it is much less than, if it's negative and large, then this exponential cuts. If it's positive and large, then this exponential cuts it. So psi by modulus cannot exceed 1 by much. On the other hand, the lower limit is very large and negative. How large? We know typical mu is 10 electron volts. Temperature would be 1 millikelvin. 1 millikelvin is 10 to the 3 electron volt. Actually, much less than that. So Kelvin is 10 to the minus 4 electron volt. Millikelvin 10 to minus 7 electron volt. So this is 10 to minus 8. Minus 10 to minus 8. So exponential to the power minus 10 to the 8 is 0 for any practical purposes. Not even write it. So I have to replace this integral, this value. So this value mu is minus infinity for any practical purpose. So I can replace it by minus infinity. So keep going. So I'm getting this expression for I. And this integral now runs from minus infinity, as I explained. Lower limit is very large and negative, can be replaced minus infinity. It's very well converging, exponential converging integral. An advantage of this change of large negative to minus infinity is that this integral now is with tabulated type. So this integral can be calculated. Because pi can be converted to Euler beta integral and calculated precisely. So it is pi alpha divided by sine hyperbolic of the same. And alpha is a coefficient at psi. So it is I pi, alpha is coefficient at I psi. So it is pi k bt. So this pi give me pi squared. Cancel this pi squared. Coefficient of alpha goes to numerator. So k cancels 1 power of k here, give me 3/2. kbt, cancel this kbt, there is no kbt here. I am adding another power b in denominator. So 5/2 becomes a 3/2. This minus I by 4 is absorbed into this exponential. Divided by sine hyperbolic of the same coefficient. And it's the end of the story in the formal part. So we'll find oscillating part of the Landau potential. We take real part of this becomes cosine, double it. This is a sum of terms. Each term oscillates in quantity 1 over b uniformly. This defines oscillation. This term doesn't oscillate. It cuts expression exponentially. So the series converges very well, converges exponentially well. I mean, the far terms of the series are exponentially small, can be neglected. So basically, it is enough to take a few terms of the series to get correct result. It's harmonic oscillations. The lowest frequency is given k equal 1. So the phase Pm mu b change 1 over b is to pi, and I find that it oscillates over 1 over b with uniform period, constant period that doesn't depend on anything, doesn't depend on temperature. It depends only on universal constant, which is Bohr magneton, and on the chemical potential or Fermi energy of the electron gas. And by the way we measure this period, you find Fermi energy, and this is how Fermi energy of most of the metals were determined from this effect of oscillation in the thermodynamic quantities that come from oscillation in the Landau potential. So I'm repeating the expression for Landau potential. So for large fields or relatively low temperature, this coefficient pi squared kBt of mu b is much less than 1. Let give you a large oscillating part. In the opposite case, if this quantity is greater than 1, the denominator is exponentially large and omega is exponentially small. To find oscillating part of the thermodynamic of the magnetic moment, which thermodynamical is minus d omega over dB, the constant T, V, and mu, and this is very simple to find, because only this rapidly oscillating part should be integrated. If it is not rapidly oscillating, it's not interesting term because amplitude is small. So when amplitude is large, it's very rapidly oscillating, and therefore, in other words, mu over mu BB is a large quantity. This is why rapidly oscillating. So only this should be differentiated, not this B and not this B. Only over this B should be differentiation. So it will replace cosine by sine and give the coefficient at B as pi mu k over mu B and B squared in denominator. I'm repeating the formula 24 from the previous slide, expression for the Landau potential, and I need to find magnetic moment changing sign and differentiating it over B. Now, B is in three places here, here, and here. However, this term is very rapidly oscillating because frequency of the oscillation is proportional to ratio mu divided by mu BB. It's enormously large quantity. Again, chemical potential is 10 electron volt and magnetic energy maybe 10 Kelvin, and 10 Kelvin is 10 to minus 5 electron volt. So this is very rapidly, it's very large coefficient here at 1 over B. Only this term should be, with our precision, only this term should be differentiated. So everything else is as it was. Cosine is replaced by sine, and I'm getting coefficient P pi m k divided by mu B. So pi and pi squared give me pi to the first power. B in denominator, instead of mu B to the 3/2, give me mu B to the 1/2. Mu comes the first power here. I think I took into account all terms. Derivative of B give me B squared and cancels with B to the power 3/2, leaving B to the power 1/2. And I get an extra K instead of power of 3/2, give me power 1/2. Everything else is without change. So this is expression for oscillating part of the magnetic moment. Now let us compare it to the case of weak fields. From the previous lecture, from formula 29, lecture 4, denoted like that. This is expression that we got for M, a general expression. Omega naught in this case can be taken at zero temperature, at zero fields. Both are much smaller than Fermi energy. So this is this expression. So I can vastly differentiate over mu, which eventually, instead of mu to the power of 5/2, give me mu to the power of 1/2. And then I can take ratio of the oscillating part to the smooth part. And it's very nicely simplifies to this expression. Let's check something. Power mu BB. So from this, B comes to the power 1/2. From this, B comes to the power 1, so 3/2, and divided by 1 and 1/2. Mu comes to the power, mu B comes to the power 1/2. Mu B will be in denominator in the power 3/2. So this is 1 and 1/2. And mu is in the first, is the power 1/2 in numerator, because here mu is the first power in numerator. This is 1/2 in denominator. So all other coefficients cancel, or are numerical coefficient another one that I'm not interested in. So I'm getting a very simple result. I'm repeating a part of equation 29 that I need. This ratio of oscillating to smooth part, magnetic moment, this is following. Now, in this expression, this ratio is always very large. Magnetic field can never be as strong, so this will reach mu. Mu is 10 electron volt in metal. And mu B may be 10
10 millielectron volt. So it is 10 to minus 5 electron volts. So this ratio is 10 to the 6. 1/2 10 to the 3. So it's a big quantity. What about this? Mu bb can easily be kBt. Under this condition, this effect will be significant, and it immediately very large. So as soon as mu bb reaches one order of kBt becomes larger, oscillations dominate. If it is to the opposite, if mu bb is a weak field, much less than kBt, then this formula is not applicable, and we know that oscillating part is exponentially small immediately. So this, despite the fact that pre-exponent is large, this term become exponential. The contribution to this, when this is large, becomes exponentially small by this parameter, and oscillation immediately disappeared. In other words, if I am increasing temperature or decreasing magnetic field, then oscillation disappears basically in a jump. I either see strong oscillation or no oscillation at all. And if I go back with the increasing field in the other order, first I see very smooth dependence on magnetic field. It suddenly changes to oscillations. This oscillation immediately becomes very strong. It's a very interesting effect. It was observed experimentally, as I will tell you. Okay, so now a little bit of history in the flow of times. I can tell you that this title is a bit sentimental. It is a copy of French expression "un peu d'histoire au fil du temps," and it is allusion to the title of famous French novel "Un peu de soleil dans le froid." It is a very sentimental novel about midlife crisis and midlife love, and it's nice. I recommend strongly to find the novel. It exists in a good English translation. Also, there is a movie with the same title. Get it? It's classic. So it's my title of this part is allusion to this title in translation to English. So let's start this De Haas-Van Alphen effect, often abbreviated as DHVA, is purely quantum mechanical effect, as we know. A magnetic susceptibility of pure metal crystal oscillates as the intensity of magnetic field be increased. As I told you, actually it oscillates in inverse magnetic field with constant period that doesn't depend on anything but on Fermi energy. The other quantity that also oscillates in specific heat is another derivative, second derivative of omega. Also kinetic effects such electrical resistivity and sound attenuation oscillate. The electrical resistivity Shubnikov-De Haas effect actually found before the Haas-Van Alphen effect. So this effect is named after Vander Johannes De Haas and his student Peter Van Alphen. And the HVA effect, as we know, comes from the orbital motion of conduction electrons in the metal. It's actually incorrect. It's combination of orbital motion and spin excitation. An equivalent phenomenon at low magnetic field is known as Landau diamagnetism. Diamagnetism comes purely from orbital motion. That we know now professionally. Experimentally, the HVA effect was discovered in 1930 by De Haas and Van Alphen, and they carefully studied magnetization of a single crystal of bismuth. Well, single crystal is important because if you look carefully at all derivation of this, it depends on momenta of electron involved in the calculation. While Fermi energy is fixed, the specific momenta depends on the dispersion of electron in crystal. It can be very complicated. And it is all in the plane normal to magnetic field because motion direction of magnetic field is unperturbed by it. For rotating magnetic field, you can look at different cross-section of the Fermi surface and get information about it. So this is after 1950, as mentioned in this article in Wikipedia. This effect got wider relevance after two famous scientists Lars Onsager and Ilya Lifshitz, in collaborations with Anna Kasevich, pointed out that this phenomena can be used to image Fermi surface of the metal. And everything we know about knew about Fermi surfaces until relatively recently, the 20 years before, when electron spectroscopy becomes the leading way to study Fermi surfaces. Information was obtained from this oscillating. So as we know, the theoretical prediction was formulated same year. Before the experiment, it was prediction by Landau, and we studied the theory. However, interesting enough, it is an interesting point of history. Landau discarded this prediction, never much advertised it or paid much attention to it. Such magnetic field needed were not yet available in the lab. It should be several Teslas. It's actually incorrect. It should be Tesla, as we know. You do not put physical unit in plural. And very low temperature. Low temperature became available, and then magnetic field became available. And actually, as David Schoenberg revealed, he asked Landau why he never advertised it and thought that experimental demonstration was impossible. He answered that that was the opinion Piotr Kapitsa. Kapitsa was experimental advisor of Landau. He was his benefactor. He got him from the Gulag, as you know. He was everything for Landau. And Piotr Kapitsa convinced him that you cannot get magnetic field. It should be very homogeneous magnetic field. Otherwise, different part of specimens will give oscillations out of phase. Because phase of oscillation, frequency and phase depend on magnetic field. So very high homogeneity of field is required. It was impractical. Well, time passed, and very soon after prediction, actual month after prediction, two scientists from the leading scientific establishment at the time, University of Leiden, and still exists, still is excellent institution for physics, found this effect. So never say that effect is unimportant because it cannot be observed experimentally. I have personal recollection of that. When I predicted with my students, it's possible to modulate phase of an ultrashort laser pulse in such a way that we will control localization of optical energy in certain nano-sized part of a metal system. I was told it is impossible to observe because the amount of light, so in the optical microscope, because the amount of light emitted from a small part is very small. We know that intensity of dipole radiation is proportional to the 6th power of the number of electrons participating in the process, square of the dipole. And if compute calculates how much light is emitted, is a very negligible amount of light. So it cannot be absorbed by light. And the near field also is doubtful because it will perturb the system. So there was a lot of experimental obstacles. And one of the outstanding physicists of our time, I would say Kit Nelson of MIT, convinced me that is a very interesting theoretical construct, will never be observed. Guess what? In about a year it was observed. Not by optical radiation, but by emission of electrons that is driven by local electric fields of a nanosystem. It was observed perfectly as predicted. So the moral is the following: if you predict something, you should not care less about possibility of observation. My answer actually was absolutely correct. I answered Kit, you know what, this phenomenon exists, and I don't care whether it can be observed or not. Eventually it will be observed by some other effect, but I will publish it because it exists. And I was absolutely right. And we still remain very big friends with Kit. We actually wrote with him proposal related to this and got grant and successfully executed it. So that is the happy end of the story. Now I will continue history very shortly. I will show you actually how the original paper looked. It looked differently from today's. It was Proceedings of Academy of Sciences of Amsterdam, published in 1930. It's a communication presented by De Haas from his name and name of Van Alphen to the session of the Dutch Academy of Sciences at Amsterdam, and this is how this paper looked in the original journal. I just took a photo of it and show it to you. So this is how science is done. And this was a new era in the physics. It's a quantum physics of solids from this moment on. So thank you. Our course came to the end.